Okay. All right. We're live, everyone. Sorry about my dogs. I'm Jen Schanger from the New Jersey Autism Center of Excellence, the Njis, which is funded in part by the New Jersey Governor's Council and the New Jersey Department of Health. We're thrilled to be here today with Dr. Brittany Travers. I want to remind everyone that we are live on YouTube right now. The recording will be available anytime after we air. I believe we have live captions enabled, and the captions will be available on the video afterward as well. If you would like to ask a question or a comment, please be sure to log into your YouTube account. And if anyone does have difficulty posting in the chat, you can also email Joe, which Joe posted his email in the chat. It's joevero@njis.us. And now I am happy to introduce our director and principal investigator of the NJACE, Dr. Elizabeth Torres.
Well, thank you, Jen, and thank you, Brittany, for coming to our center and enlightening us with your latest research. We're very, very lucky because Dr. Travers is one of our rising stars in autism research. She follows this multi-layer, multidisciplinary approach to autism, and it's teaching us a lot of new things that we should be familiar with, and integrating multiple layers of knowledge. Which is the way that such a complex problem, such complex research endeavor should be undertaken. So Dr. Brittany Travers is an associate professor in Occupational Therapy Program at the Department of Kinesiology at the University of Wisconsin-Madison. And her work is inherently interdisciplinary. She earned a Bachelor of Arts degree in psychology and Spanish from Creighton University, and a master's in arts and a PhD in cognitive psychology from University of Alabama, and completed postdoctoral fellowship in intellectual and developmental disabilities research at University of Wisconsin-Madison. Her overarching program of research housed at the University of Wisconsin-Madison, the Weissman Center, focuses on the intersection between sensory-motor skills and neurobiology in autism and non-autistic individuals. She focuses on how motor development may serve as a window into neuroanatomy, core symptomatology, and skill development. This line of inquiry has led to a strong interest in the brainstem. She also examines how motor challenges impact daily lives and occupations of autistic and non-autistic individuals, and whether novel interventions targeting motor skills can enhance quality of life. Her research combines brain imaging, such as magnetic resonance imaging MRI, diffusion weighted imaging DWI, with quantitative measures of sensory motor function, cognition, and daily living skills in autistic and non-autistic youth. And her talk today is going to tell us about motor differences commonly reported in autistic individuals that may be one of the earliest signs of autism in the first year of life. However, the daily life impact and neurobiological basis of motor differences are not clear. This talk will with distinguished speaker Brittany Travers will discuss motor differences commonly reported in autistic individuals, links to the early developing brainstem, and links to daily living skills. We will also discuss the behavioral and structural imaging outcomes of a randomized controlled testing, trial testing, a biofeedback-based balance intervention in autistic youth. And without much ado, I'll give you Dr. Travers, and welcome, and we look forward to your talk.
Thank you so much, Dr. Torres. Thank you for the invitation to be here. It's really exciting to get to speak with you all about this research that we have been working on. As Dr. Torres said, We are going to be talking today about motor skills and early developing brain structures like the brainstem in autistic individuals. I'm going to throw in a couple of slides on some sensory aspects too in the relation to the early developing brainstem. So maybe that'll be a little bit of bonus material outside of the motor context, but we did so because sensory and motor are so integrated. So I want to start out by saying thank you so much, particularly to the participants and their families who've made this work possible. In the randomized control trial that I'm going to talk to you about today, participants and their families had to come to the lab 3 times a week for 6 weeks, which is a huge commitment. And I'm so, so grateful to them for making that commitment. I also want to thank the Motor and Brain Development Lab. So these folks are really the backbone of everything that we are doing. I also have the privilege and pleasure of working with some amazing interdisciplinary collaborators, both here at UW-Madison, but also at other universities as well. I would love to thank our Community Advisory Board of autistic individuals and their family members who look over our research, who have given us such amazing insights in their interpretation and what measures we should be using going forward, and how we can continue to make our work that much better. And then I also want to thank the funding agencies who made the work that I'm going to talk to you about possible. So I'm sure with this crowd that we all have a pretty common understanding of autism, but according to the DSM-5, autism spectrum disorder is diagnosed in the presence of social communication difficulties and/or restricted or repetitive interests and behaviors. And here I have the symbol for neurodiversity, which I personally love in thinking about the spectrum of autism. Now, when I first started doing autism research, I was told and taught that we should really be using person-first language, so person with autism. But in the last couple of years, we've been hearing from autistic self-advocates that the majority preference is identity-first language, so autistic person. And I really think it's important to be aware of the language that we use to describe the populations that we study. So in today's presentation and our work, we are going to be using identity first language. But in the same breath, I would like to acknowledge that one set of terms can't encompass the personal preferences of all members of the community. And if the community preferences change, the commitment of our lab is that we are going to do our best to change with that. Okay, so with all of that said, I want to take you through just kind of a 30,000 foot view of how we think about our research, so our research framework. So we get to think about this amazing brain that all of us has that allows us to do so many incredible things. And maybe one of the most incredible things is it allows us to develop skills that, that then enable us to interact with the world around us. So we have our brain that enables motor ability and motor development across the lifespan. And then motor skills also then can translate to us being able to engage in everyday tasks that allow us to have our needs met. So when we're thinking about autism in our lab, we're thinking about it as a neurodevelopmental condition that may have cascading effects on motor ability and also daily life experiences. So in today's first part of the talk, I'm going to be talking about motor differences in autistic individuals, and then looking at what relation that might have with daily life and experiences. And then in the second part of the talk, I'm going to be talking about some of the brain mechanisms we've been examining to think about why are there these motor differences in autistic individuals. And then in the third part of the talk, we're going to be talking about an intervention, a randomized control trial that we tested to ask, can we actually change this cycle? So can we use movement as a way to engage our brain, to change our brain? And will that have cascading effects on motor ability and the ability then to engage in daily living activities? Okay, so with that said, let's go ahead and launch into part one and think about motor differences in autism. So motor differences were noted in the very first report by Leo Connor of autistic children. And since then, we have found that motor differences are highly prevalent. So it's estimated that up to 87% of autistic individuals also have some type of motor difference or motor challenge. We also know that motor differences may be one of the earliest predictors of an autism spectrum disorder diagnosis. And we know that motor differences are reported in multiple domains. So postural control, maximal and precision grip strength, reach to grasp tasks. So it's not that these motor differences are domain specific. We also know from the literature that motor differences are able to distinguish autistic and non-autistic individuals. And one of these studies comes from Jonathan Delafield-Butt's lab in looking at how playing on an iPad-like tablet was able to demonstrate that autistic children touched the tablet with greater force, had faster screen taps, and had faster, more variable and larger gestures on the screen. And those differences were actually able to predict who had already received an autism diagnosis and who hadn't. We also know from Dr. Torres's lab that goal-directed reaching is able to distinguish between autistic and non-autistic children, and also relates to symptom severity profiles within the autism spectrum group. So this is kind of one slide overview. When I first wrote this talk, it was actually 5 slides. So bear with me as I've tried to condense this to make sure that we have time for questions and everything today. But one of the things that I think is really important and why I choose to focus on motor features is that motor skills are related to daily living skills. And this is not only in autism, but this is also in neurotypical individuals and, really all individuals. And if you think about a lot of the tasks that we do in our daily life, even speaking, writing, cooking, a lot of those have a high demand on motor control. And we see these relationships between motor skills and daily living skills really across the lifespan that have been investigated. In our study, which I think to date is the only longitudinal study looking at this, we found that in autistic children, adolescents, and adults, the grip strength and finger tapping skills were able to predict concurrent daily living skills, and then also predict daily living skills 5 to 9 years later. So we're really interested in motor skills and thinking about how those might facilitate daily living tasks. But one of the questions I keep having is exactly how and what types of movement and motor skills are necessary for these specific features. So how do we get a better look at the causal piece of the motor impact on daily living tasks? And to investigate this question, we developed a novel task using a Kinect camera and a Wii balance board, and we call it the MRAD, or the Motor Rain Suit Assessment During Dressing. And so the child is fully clothed, but we're measuring dressing here by having them put a clear rain suit on top of their clothes, and then measuring their movements, how their every part of their body is moving, and then also looking at how they're able to make postural adjustments during this task. And the reason we chose dressing is because that has been highlighted as a daily living skill that there are usually group differences in the literature. And indeed, when we looked at this in 36 autistic youth, so between the ages of 6 to 18, and then 29 non-autistic youth, what we found was that there were really large size group differences in the length of time it took to dress, even when we had standardized the rain suit aspect of this task. So it wasn't just the clothes or the environment. It really seemed that there are these group differences. So then we wanted to dig in and ask why? Why are there these differences? And so as part of the Kinect camera and the Wii balance board, we collected lots of measures. And I'm showing you here a really wonderful collaborator, Adele Ardalan, who was a grad student at UW-Madison when we started this work, but who's now a postdoc at Princeton. We continue to collaborate, and he's helping us really make sense of a lot of these measures. But from the balance board, we collected measures of center pressure path length, so how one's balance is moving left to right and forward to back. We also looked at center of pressure ellipse area, which is just how much of the board is used when it comes to postural shifts. We looked at center of pressure variability, and then Adele had the idea of creating another measure, which was this center of pressure spatial components. So how many unique components across this task are there in the way that people have shifted their weight on the balance board during dressing? And then from the Connect camera, we gathered information from 20 joint dots, and that was collected every 6 milliseconds in the X, Y, and Z direction. It's a pretty large data set here. So we looked at X, Y, and Z variability. We also, from the literature, thought that we should be looking at spinal tilt, or how tilted or straight up a person might be during this task. We also wanted to look at knee to shoulder ratio and thinking about what it takes to bend over and get pants on and things like that. And then we also looked at rotational degrees of freedom. And so this allowed us to look at joint movements in relation to each other instead of as kind of a unique point. So tons and tons of movement measures that we were collecting here. And we really needed to funnel these down to try to make a little bit more sense and to figure out what movement properties actually distinguish autistic from non-autistic individuals during addressing task. And our first attempt at this was to actually see what movement during dressing looked like in a non-autistic adult cohort of collegiate trained dancers who we presumed would have good motor skills to be able to accomplish this task versus people who did not have any dancing or at least collegiate level dancing backgrounds. And so our first step was to look at which of the variables that I showed you on the previous slide actually differed between our dancers and the non-dancers during the dressing task. Then the second step was to see which of these measures differed in the autistic versus the non-autistic individuals. And then finally, we went one step beyond to actually see which of these measures predict dressing task length, and can knowing what these movements are like, can that actually explain why there are group differences in dressing times? So again, here's our list of tons of movement measures, and I'll be really quick with this, though. Basically, these were all the ones that we were able to eliminate, either by there not being differences between dancers and non-dancers, or there not being differences between the groups. So what we were left with our We Balance Board data was only the center of pressure spatial components data. And then what we were left with our kinematics data were 9 joint dots, which you can see on the figure in the upper right-hand corner. And we were only looking at the Y variability, so the up and down variability. And what I'm going to show you now are the differences between the autistic and the non-autistic participants. And those are shown here with the dark arrows. So we did see pretty large size group differences in our postural stability spatial measure, as well as in the left and right knee, the left and right hip, the shoulder, that's particularly the left shoulder, the head, the torso, and the waist. So what's really interesting here is that the autistic participants on average tended to have fewer number of spatial components, so potentially more blurring of the different spatial properties in their postural stability measurements. And then here we actually found that there was less variability or less variance in the autistic group compared to the non-autistic group on this task. So as I mentioned before, we took this one step beyond. Like, group differences are great, but can we actually explain this relationship between diagnostic group and the length of time that it took to dress? And what we found was that only one of these measures had an indirect effect that would mediate the relationship between diagnostic group. And it was a full mediation. So once we knew about this measure, it actually took away the relationship between diagnostic group and the length of time to dress. And that measure was, again, that postural sway spatial configuration measure that Adele had thought up. And so as a summary, because I know that this is not your typical motor measure that we have here, but here we have the length of time on the y-axis that it takes to dress. And then here we have on the y-axis the number of postural sway components. So you can see that there are strong associations, and that there are also then these group differences in this particular measure. So the way that we interpret this is that autistic youth showed fewer distinctive postural adjustments during dressing, which then predicted performance on the task, which we had as the length of time to dress, and also accounted for group differences in performance. Okay, whew. So I know that's a lot of information, but here's a couple of key takeaways from that first part. And the major thing is that, motor features do appear to be highly prevalent in autistic individuals, and motor features appear to be linked to poor daily living skills. And then what we're finding is that particularly in dressing tasks, that distinctive postural adjustment piece was the only movement measure that seemed to actually account for why there were longer dressing times in autistic individuals, which suggests that that might be a target for occupational therapy or physical therapy in the future. Okay, so now the next question for part 2 of this talk is, what is the brain basis of sensory motor features in autism? And I'm going to tell this a little bit in terms of my journey in trying to understand this relationship. So I was at the University of Alabama, and I was doing, autism diagnostic trainings, and I was told to focus on things like social communication, eye contact, things like that. But I kept finding myself so distracted by how people were moving in space. And so my advisors very kindly allowed me to include a postural stability measure in my dissertation. And I had actually hacked into my Christmas gift that year, which was a Wii balance board, and looked into how we could get it to calibrate and then collect data for us. And so in this, in my dissertation study, we found that the degree that a person was kind of wavering when asked to hold still on the balance board was highly associated with the degree of severity on core autism symptom severity measures. And this was kind of shocking. So why would we have these relationships here? And really, quite fortunately, a lot of labs at the exact same time started publishing similar findings. So we knew that we weren't alone in this. But it was interesting how different people interpreted these different findings. So there were some groups who suggested that motor difficulties may be something that cause core autism symptoms. So thinking about like ocular motor control, so being able to control your eye movements as something that may impact joint attention or social communication with a communication partner. And that seemed plausible, but we also know that there's children who have motor difficulties in infancy who do not go on to receive an autism diagnosis. So it seemed probable, but maybe not, a one-to-one relationship. There were also folks in the literature who were suggesting that it's actually core autism symptoms that may be impacting motor features in autism. And so, very broadly, the idea was that if a person is not really interested or drawn to looking at other people around them, then they may miss out on seeing how people do certain motor tasks. And so things like, cooking or tying your shoe or riding a bike, which are all pretty complicated that we oftentimes look to other people to learn, may not come as easily. And this seems feasible as well, but in our study, we were looking at really foundational postural stability measures, which didn't seem like it would really rely on looking to other people to be able to perform. So in our work, what we started thinking about was, is there potentially a third variable that could explain to us why core autism symptoms and motor difficulties seem to be linked? And in our line of work, we kept thinking about this in terms of the brain and the neural substrates. And my favorite example of a third variable, and this is why, correlation does not equal causation, but is that of the link between shark attacks and ice cream consumption. So there's a strong correlation between the two. But once you take into account summertime temperatures, which is the third variable, there's actually no longer a relationship between core autism symptoms and motor difficulty, between shark attacks and ice cream. And so we were thinking the same thing could be the case in core autism symptoms and motor difficulties. So I want to just briefly touch on the methods that we use for brain imaging in our work. And so we have had great success in making the MRI scanner environment something that can be quite comfortable for kids, both non-autistic and autistic children. And while they're in the MRI board, this is actually my son hugging Bucky the Badger going into the MRI scanner, we can get pictures that look something like this of the brain, and that can distinguish between the white matter and the gray matter of the brain. And I'll tell you a little bit how this works. So what we're looking at with this is how water is diffusing throughout the different tissues of the brain. And so if I were to take a little cube of our brain image here, and this is in the ventricles where it's all cerebral spinal fluid. And so we have water molecules in the ventricles and in this little voxel cube. And because there's nothing to restrict the diffusion of water, those water molecules are going to be going all over that voxel. However, if we move into the corpus callosum, which consists of a number of highly myelinated, so fat-covered axons that are almost like the highways of the brain, what happens is the water molecules can't pass through those fatty layers of the myelin. And so the water molecule and its diffusion and movement is restricted along that white matter track. And from this, we can model it using ellipsoids. And if we build the brain back, voxel by voxel, cube by cube, what happens is we can get images like this that can tell us about the directionality of these white matter fibers and about the microstructural properties within those white matter tracks. So as a postdoc, I was actually able to work on a study where we had motor measures. They weren't postural stability, but it was grip strength. And what we found was that grip strength was indeed related to autism symptom severity within a cohort of approximately 100 individuals. And what we did next to try to, because we were in search of this third variable in the brain, is we started thinking about the white matter tracks that are associated with a person's grip strength. So these really motor dominated white matter tracks. And there was one bilateral white matter track that was indeed very predictive of grip strength. And it was the brainstem's cortical spinal white matter track. And that is a primary output track, taking motor commands from the cerebrum and the brain, going through the brainstem and out to the body. So what we did next then was to see, well, does this track actually relate to individual differences in autism symptom severity? And actually, quite surprisingly, it did. And not only that, but it actually took away the relationship between grip strength and autism symptom severity, which suggested this was indeed a good candidate for a third variable in this relationship. So if we knew the microstructural properties of this brainstem track, we could predict both grip strength and autism symptom severity and take away the relationship between the two. So I was excited about this finding, but also honestly, so scared and nervous because it was in the brainstem. And I kept thinking, well, maybe we need to look outside the brainstem. So what we did is a search of the entire brain to see where symptom severity measures were correlated, and then also where motor measures, our grip strength measures, were correlated. And indeed, it seemed really specific to the brainstem. So we did feel like this was a brainstem specific process or finding. And this took us down pathways that I never thought we would ever explore. So much of my training and the training, I think, of a lot of people had been focused on the cerebrum of the brain. And sometimes even just like, don't pay attention to the brainstem. It does really cool things, but it's a really complicated area. And here we found that our findings of this were actually in the brainstem. And so we did a deep dive to really try to better understand, what is the brainstem all about? And we now know that the brainstem is one of the most early developing and early myelinating brain regions. It is involved in things like attentional orienting, so what captures your attention or not. It's involved in really fundamental motor skills, vital functions like respiration and heart rate, and also sensory gating. So what information comes in and what information doesn't. I was also surprised to find that the very first biology-based theory of autism by Bernard Rimland in 1964 actually posited that the reticular formation of the brainstem was consistent with a number of autism symptoms. And what's really striking about this is in part the history that this theory happened at a time when the predominant theory was refrigerator mothers causing autism. So one of the challenges though with this is that a lot of this work to test his theory had to be done in postmortem tissues. And when you have the postmortem tissues, then you aren't able to actually then go and see exactly where the individual differences in sensory and motor features might be. So in part, we have been able to come up with some technologies with MRI to actually hopefully be able to answer this question a little bit better. We also know that oral sensitivity is associated with brainstem volume. And there's a host of epidemiological, behavioral, histological, neuroimaging, and animal evidence of brainstem contributions to autism. And so I have a couple reviews here, but there's actually two that came out, I think, in January that are also fabulous, thinking about the very complicated, beautiful brainstem and how it might be related to a lot of different autism features. So this really has gotten me thinking about, some of how I had previously interpreted some of these early signs of autism. So some of these early signs of autism are things like lack of appropriate eye contact, lack of response to name. And I used to think about that as a social communication thing. But what if, in terms of the brainstem, this was actually attentional orienting? So what captures one attention or simply doesn't? And then things like lack of shared interest or hyper or hyposensitivity, maybe those are more representative of sensory gating differences than some type of pathology as you see here. And then you can see lack of gestures, delays in motor development, maybe that's in part linked to some of the brainstem aspects that we could be looking at. So we were really excited to launch into really trying to better understand the brainstem, but we were also nervous because what we found out was that there are so many technological obstacles that really have limited the examination of brainstem contributions to behavior in humans. So there are epidistortions, which can either stretch out parts of the brainstem or condense them, which you can see a little bit here. And we needed to find ways that we could get even better precision of these brainstem tracts without that stretching or smushing of the brainstem. And so we were able to work with biomedical physicists to help us come up with a better protocol that really optimizes the brainstem regions. I think it was last month, or at least in the last 2 months, we also have come up with post-processing improvements that even help us better delineate the brainstem and brainstem substructures. If you think about it, the brainstem is very anatomically different than the rest of the brain. And so my argument is that it really does need to have more specific types of way of imaging it, because in the cerebrum, the white matter is all together and then it spreads out. But in the brainstem, it's weaving around these gray matter nuclei. And I think that we need to have more precision in being able to delineate that, which we feel we were able to do here. And we did some tests and found that this was more biologically probable with our new processing pipeline, which we call tidy fused. So taking this tidy fused data, this brainstem optimized data and brainstem optimized process, what we did is we set out to look at how the brainstem and its white matter tracts may be related to sensory and motor features and also to core autism features in both autistic and non-autistic children. And I'm actually really excited to show you some of these first results. These are not yet peer reviewed, so I'm always looking for feedback as we go through this, as we go to draft the manuscripts. And so we're going to be focusing on this first aim, which is the sensory and motor features. So our methods were we have 134 participants between the ages of 6 to almost 11 years old, and 53 of whom are autistic. We have our brainstem optimized protocol, which then also went through the brainstem optimized processing. We had a caregiver report sensory assessment, which is the Sensory Experience Questionnaire 3.0 by Grace Baranek. And then we also conducted a standardized motor assessment, which is the Breuning-Otsaretsky test of motor proficiency. We delineated the brainstem into 23 of its different white matter tracks. So these white matter highways of the brain that facilitate communication between different brain areas. And we got that into, we were able to graft all of those regions into the individual images of our participants. So what we did first is we looked to see within the autism group, do these brainstem tracks relate to the sensory features? And what we found was that indeed, yes, particularly brainstem input tracks were related to the sensory features in autism. And these tracks included the medial lemniscus, which is a track that takes information, sensory information from the body and up to the cortex. We also had the middle cerebellar peduncle, which takes information from the pons of the brainstem and sends it through to the cerebellum. And then we had the inferior cerebellar peduncle, which takes information primarily from the medulla aspect of the brainstem and takes it into the cerebellum as part of a feedback loop. We then followed up and said, okay, so are these tracks also related to sensory features in non-autistic children? And we found no, that really these brainstem tracks were uniquely related to sensory features in autistic children. So again, we had this question because we wanted to look just at the brainstem here, but okay, is this actually representative of something outside of the brainstem? So we did a follow-up analysis of the whole brain. And what we found was that even though our brain mass in the brainstem and cerebellum was only 7% of the total brain mass, 69% of our findings were in the brainstem and the cerebellum. And so while there's some other areas like in the thalamus and even in the parietal occipital areas, excuse me, that the majority of these findings in autistic individuals were indeed in the pons and midbrain area and the cerebellum. So then we did a parallel analysis, but with our motor information. And what we found here was that two primary motor output tracks, the frontopontine tract and the cortical spinal tract, were associated with individual differences in motor performance in the autistic group. But similar to the sensory analyses, what we found was they were not related in the non-autistic group. So again, these brainstem output tracks being related to motor performance really did seem to be unique to autism. You'll have to excuse me if I have an animation error on this next slide, but bear with me. So I've covered a lot of ground here. And if you all are anything like me, the brainstem is a very complicated space. And I had to take a lot of time to really try to dig into what the brainstem actually does and the neuroanatomical properties of the brainstem. And I've kind of glossed over it here a little bit more, but would be happy to talk more with you all about it. But the first part two key takeaway is that the early developing brainstem may help explain some of the motor features, symptom features, and sensory features in autistic individuals. The other is that we kept finding that more restricted diffusion within the white matter tracts related to more sensory features and lower motor performance, particularly in autistic children. And typically we think of more restricted diffusion as a good thing, like, oh, these myelinated tracts, they're taking up much space and so the water can't diffuse as much. But here we're actually seeing that the more restricted diffusion is related to more elevated sensory features and lower motor performance. And so we have some work to do here to really do some other additional quantitative MRI techniques to understand the neurobiological basis of why we have this finding. And then finally, for part two, we have that brainstem white matter uniquely relates to sensory motor features in autism. And the location of these findings in the brainstem, to me, highlights the reflex-like nature of sensory responses in many autistic individuals. And this really fits with a lot of what autistic individuals have said, that a lot of these responses to aversive sensory stimuli are reflexive in nature and hard to control. And I think that one of the things that these findings does is it really makes us think about the interventions that are used to potentially target some of these sensory responses. And some of these interventions use reward or punishment that kind of assumes somebody might have control over some of these things, when these brainstem findings suggest that this might be quite reflex-like. So I'm going to end with this, can we change this cycle? And I'm going to go through this pretty quickly because I know that we're running out of time, but this was our randomized control trial. And one of the things that we saw, or that we know in the neuroplasticity research in the last 2 decades of this research, is that learning new motor skills and practicing them over and over and over again may be a particularly effective way to actually impact the structures of the brain. And this is because we not only have to have a representation of ourselves, just standing or sitting or being at rest, but we have to have separate representations of ourselves in our brain for every activity that we do. And we do a lot of activities oftentimes, right? Think of all the different ways that your mouth moves to form words, for example, which isn't even represented here. And I was really inspired by this 2010 paper that in non-autistic college students found that intensive balance training actually was able to make changes to the white matter in some of these key areas that I had talked to you about before, like the cortical spinal tract. And I was really excited about this paper, and it led me to think about, okay, well, what about in autistic individuals? So we set out to study, can motor interventions impact behavior in the brain in autism? And so think about motor intervention as intensive balance training. And could that potentially have improvements for balance, symptom severity, daily living skill improvements, and also changes in brain wiring? And so we developed our video game-based balance training with visual biofeedback, which is such a mouthful. So if somebody has an idea for how we can truncate that, I'm all ears. But we use traditional Tai Chi and yoga poses, and participants are able to hold these poses anywhere from 5 seconds to 2 minutes at a time. And so here is an example of me doing one of these poses. And so I see myself on the computer screen, I step into the shadow, and when I'm in the shadow, all of my joint dots turn yellow. And then I will dip out of the shadow here, and I'll immediately see which part of my body is outside of the shadow. And as I'm doing it correctly, there's a green light at the bottom, and there's also the background revealing itself to me. And while participants are doing this, we're able to collect the kinematic data and also the WeBalance board data from this. So our first attempt in looking at this was in 29 autistic youth. And what we did was 6 weeks of training, so 18 sessions total, and an hour of the training I just showed you. So this would be a person standing on one foot up to 4 minutes at a time, and then switching to another foot, standing on that, and going for a full 30 minutes. We give them a little break in between, and then going again. So it is a very intensive balance training, and we thought we needed it to be that way to actually see if it could change the brain. And at the first session, we did balance testing. And then here's a little bit more of the description of the training sessions that I just verbally gave you. And then at the last session, we also did balance testing. What we found from this first study, which didn't have a control group, was significant in-game improvements, both in the 2-footed standing progress and in 1-footed standing progress. So up to a 1.72-fold increase in balance times for all of the autistic participants. And I do have each individual line here because I just want to represent that there is a lot of individual variability in these trainings. Not only did we see in-game improvements, but we found that these in-game improvements actually predicted out-of-game postural stability in the eyes open standing, the eyes closed standing, and the visual feedback standing measures that we had. So we felt like this training actually did translate to a task outside of the game. And then we also had asked participants, what did you think about these games? And here are some of the quotes. I became so tired and painful, but it helped me to balance more. I mastered all of them. Can't wait to try it in sports like tennis or soccer. And this is from a parent. He hadn't played video games before. Now he operates a TV remote with increased dexterity. There's also less hesitation in trying new physical activities. And then the last one was very fun. Got to meet a lot of people, made me think in a different way. And I think that it's really important for us to ask if these, interventions are indeed enjoyable of our participants. And it was great to get some of this feedback. So we saw from the study that improves balance was generally enjoyable, but there so many questions remain, like what brain areas explain the balance changes? Can balance training actually have cascading benefits for the brain, autism symptom severity, and daily living skills? So we did a randomized control trial where we did a pre-assessment of diagnostic and postural stability stuff, including a magnetic resonance imaging scan. Then we randomly assigned participants either to the balance training, which I just described to you, or a sedentary control condition, which was matched on as many variables as we possibly could. So in the sedentary control condition, they came to the lab the same amount of time with the same research assistants and learned to get better at a video game called Flow and Osmos, which was matched on the visual speed of graphics. And then we did a post-assessment, which was a follow-up postural stability measure and follow-up MRI scan. And then we had some primary outcomes that we had to specify before we even started the study, as well as some secondary outcomes in terms of autism symptom severity and daily living skills. So here's a breakout of how our random assignment worked in terms of both autistic individuals who were in the balance group, non-autistic individuals in the balance group, autistic individuals in the control condition, and then non-autistic participants in the control condition. What did we find? Again, we found that balance training led to improved balance inside and outside the game, so that there were longer balance times up to a 36-second improvement. And one of the questions we get is, what is a clinically significant improvement? And honestly, we don't know. I don't have a good answer to that. But we do think that, 36 seconds additional ability to stand on one foot could prevent a fall on the ice or even stepping into a tub. We also saw almost identical balance gains between the autistic and the non-autistic group. And this was really exciting. So even though the groups started at different points, the amount that they progressed during the training was virtually identical. And this is exciting because there was one reviewer many years ago, as we put this grant in, who said, we don't even know if autistic individuals can improve their balance. And not only were we able to show that, but we're able to show that it's at the same rate as their non-autistic peers. We also found that balance training led to decreases in autism symptom severity. So this was the social responsiveness scale. This is their overall score. And you can see here at the very top of the graph, I'll try to get my cursor there, that this X is the autistic individuals assigned to our balance training group. And they're nearly identical at the beginning of the study as the autistic individuals who are assigned to our control training. And here you can see only the balance training group goes from the severe to moderate place. However, we did not find changes in daily living skills. And oh, did I want this? I thought that this would be a fabulous thing to find. But in this 6-week period of time, there were no differences in daily living skills. Long story short, we parcellated this entire cortical spinal tract all the way from the brainstem to the cortex, and we looked at it layer by layer by layer, but we did not find that this balance training actually showed any changes in this cortical spinal tract. So we asked the question, where, if anywhere, did the brain change? And we used a slightly different technique than what I told you before. So it's still looking at water diffusion, but it's actually able to parse apart the different tissue properties and then think about how much wiring, so how much volume of like axonal and white matter volume is there compared to how much dispersion of the wiring. So if you're learning new skills and new connections in the brain are being made, we would expect there to be a higher degree of this intracellular volume fraction, so more white matter. And we'd also expect there to be more spread in how these white matter tracks are connected. So here was the big neuroplasticity question. So which areas of the brain, if any, changed as a function of balance training? And I do want to point out that this is a very rigorous test because each person served as their own control, so pre and post. And we found that the balance training group showed changes in areas like the superior cerebellar peduncle, which takes information from the cerebellum and sends it up into the brain, the sagittal stratum, which has been associated with sensory motor features before, and then also the cingulate gyrus. And the next step was then to examine whether these balance training brain changes were consistent across the autistic and the non-autistic groups. So were the brain responses in autism and non-autism similar? And what we actually found was that there was a lot of differences. So although the behavioral improvements and balance were nearly identical between the autistic and non-autistic groups, the brain areas responsible for these behavioral changes were often distinct. Specifically, the non-autistic group who underwent balance training showed the anticipated increases in ICVF and ODI, so that volume and spread measures that I talked about, whereas the autistic participants potentially showed a more diverse spread of how their brains changed during this finding. So we are doing follow-up analyses to better understand the diversity of brain responses within the autism group. One key thing that I want to point out is that there was this area in the brain of the superior cerebellar peduncle, which again takes information from the cerebellum and sends it up to the cortex. And while multiple brain areas were involved, this one area was really found across multiple analyses to be related to changes due to balance training and also changes in the measure of autism symptom severity. So here's kind of our what we found. We found that this video game balance training improved balance, made changes to autism symptom severity, did not change daily living skills, but changed some aspects of brain wiring. But while there was some overlap, it was largely distinct in the autistic individuals. So some of the key takeaways is that balance training may be an effective method for improving balance and decreasing parent-reported autism symptom severity. But we really want to study larger sample sizes with this question. Also, it's been brought to my attention that symptom severity may not be a meaningful measure and a meaningful measure of change. And so in the future, we want to study quality of life and other measures that are more meaningful to the autistic community. We also want to study what are the lasting effects of this training, because we were able to do that in this current one. The other thing is that, and this is consistent with the sensory and motor brainstem relations I showed you earlier, is that the brain may be wired differently in autism, such that similar behaviors like improvements in balance times may rely on distinct brain mechanisms. So in our future work, we are going to be really looking into that superior cerebellar peduncle because there was some really interesting findings there. So I know I've given you all a lot of information. I want to thank you so much for your time and attention. I would love to hear comments, feedback, questions, anything that I can help clarify, any responses that you have to this work. So thank you so much.
Thank you so much. We do have a couple of questions already, which
Great.
I love to get to. Okay, so first of all, I want to tell you that there's the Autistic Strategies Network, which is in South Africa, is here and planning to share this within Africa, with another states in Africa as well. And so I'm going to get to their comments in a second. But first, I'll start with one from Femme Intangible, which is, does speech production have anything to do with this, or it depends? My child has no motor difficulties, never had, but she struggles a lot with speech. Can motor difficulties be present with separate groups of muscles? And also she adds, she has no problem with feeding muscles, so makes me think it relates to something else. And I'm sure you both are going to have a lot to say on this.
Yeah, I will say, so I'm not a speech language pathologist. What I do know is that speech is considered the motor act of language, and it's incredibly complicated. There's some amazing MRI videos of watching people say words, and you see all the motor movements that are happening in the throat, in the mouth, the palate, the tongue. It's really incredible. And so it would make sense that it's possible to have challenges with a specific motor component like speech and not with some of the other pieces. So it's theoretically possible. We have not looked specifically at speech and how it relates in our study. But Dr. Torres, do you have thoughts on that?
Yes. definitely a very strong motor component, definitely separable in the ganglia innervating the trigeminal ganglia and the from the neck up versus from the neck down, and the maps are different in the spinal cord as well, and the afferent fibers are different. We have studied patients that, in particular, our patient Ian Waterman, who had a viral infection attacking the afferent fibers from the neck down. He couldn't feel pressure, touch, or movement, and the viral infection spared pain and temperature fibers, but in the face they were spared, and so there was a complete dissociation between the sensations in the face and the muscles and the muscle tone and so forth. And one aspect, so a lot of people say my child doesn't have motor issues, but one aspect that we find is that a lot of the motor issues are invisible to the naked eye. And so you can catch them with instrumentation, and then you can see that there is a problem, where there is muscle tone or hyper spasticity or tremor, invisible tremor that you're not catching up with the naked eye. But more importantly, is the moment-to-moment fluctuations in the motor code that constitute a form of feedback, of kinesthetic, and we call it kinesthetic reafferent feedback. And that impacts everything that we do, whether it is breathing, talking, yawning, walking, reaching, anything that is goal-directed, automated, spontaneously happening from central pattern generators versus top-down precision, cortical-driven control and planning. So definitely it could have a component, a motor component. Our techniques don't always catch, so there is always what we call the dark matter of science, and it's the part that we're not catching with our techniques. Whatever it is that we're doing, the caveat is that we're leaving a lot out. So we can only speak of what we measure. And there is a lot of it that we do not see and we have not measured, but that doesn't mean it's not affected. So
such a good point. And Dr. Torres, I think I have an example of that in this. I have some follow-up slides, so bear with me, but we actually have some movement property. Oh, here we go. So here are two videos that you can see at the bottom of the screen that we've actually measured. And this is from a study that I think was from 2019 in Scientific Reports. And one of these, they're both age-matched adolescents, but one has an autism diagnosis and one doesn't. And it's very hard to kind of pinpoint. But what we were able to find is that looking across multiple individuals and multiple videos of this, we were able to distinguish with 89% accuracy those who had autism and those who didn't. But I think that even when you look here, you might have a guess, but it would be really hard to pinpoint exactly where that is. And if you all are guessing it, the person in the middle, towards the middle of the screen, is the one who has a previous autism diagnosis.
Excellent. Yeah, that illustrates the point quite well. I found your talk amazing. It's so much information, and it's all so good, and it confirms so many things that that people are commenting on, and that the community has always been saying. And these are not bad or inappropriate behaviors or anything like that. A lot of it is inevitable. It's not meant or intended. It's just you can't help it. And we come across these things as we age ourselves. It's the motor systems that begin to decay as we age, and then we begin to see some of the things that we see when there is no when the neurodevelopment is different. But it's very nice. So one thing that I really found remarkable with the heterogeneity of autism, that you see these common convergence in the brainstem and in the motor code. And it's something that we also see in our research. And I think that's why motor has been a missed opportunity in autism, because it's this convergence that no matter how heterogeneous it is, you do see this differentiation, and you do see a way to identify target for treatments. In your talk, you identify at least 2 targets for treatments that I can remember. It was a lot, but that I can see. And you can also identify similarities, not just target for treatments that you can bring, but also similarities will give you an entry point on what it already is working at the natural, at the sort of neurotypical level. So
yeah, and thinking about the strengths with that too,
yeah,
right? Like
exactly,
we all have our strengths
exactly
within that, and how do we play to those motor strengths?
Yeah.
Yeah.
And a lot of the research doesn't look at the similarities because they don't get a p-value that is significant or whatever. But that's an entry point. When you have something that is similar to the neurotypical system in the motor domain, that's good news, because that's an entry point in your intervention. And then the last part of your talk, when you close the loop. So most of the research in autism is open loop. You describe a differentiation, but this trend of actually closing the loop and bringing the motor component as a feedback element that then intervenes naturally is causative, because it's self-generated and it's self-monitored, and the system learns how to self-regulate itself. And it's causative, and it gives the necessary autonomy, because it links actions and consequences in natural way that the person's in control. So I think this type of research will have a tremendous impact in the community that designs therapies and that is currently intervening, because now it's an intervention that is monitored carefully and with precision, given these tools that you're showing us.
Yeah. And some of the feedback before as well was how refreshing it was to hear you prioritize whether this was enjoyable to the autistic people that you were working with, because, that's such an important piece that, again, has not been prioritized for the most part. And, the fact as well of, are these measures important, to these people? And so one of the comments from Tanya at the Autistic Strategies Network earlier was that dancing helped her a lot as an autistic person with both balance and coordination. And like Liz, you've talked a lot in the past about how later in life, especially, as we all age, falls can become a problem, but that, it seems even more prevalent in autistic people. And so I'm wondering,
and earlier in time, earlier in age. Right. Yeah.
So I'm wondering, like, what are like more potential suggestions that you think could be helpful to someone's motor system, that could maybe help prevent.
Do you want to take that, Brittany, and then I'll go after?
Yeah, that sounds wonderful. So the way that I think about this is, I wish I had lifetimes to test all these different ways of moving, right? Because I don't have data to suggest that dance is going to be the thing, right? But from the neuroscience literature, it's all the different ways that we move and learn and practice movement. That is something that's really a great thing for us and great thing for brain health. And so for me personally, I try to find the ways that I can move the most joyfully. And I've had a lot of trial and error in that, like, ooh, not trying that again, but Zumba, maybe, like, let's go that way. Right. And so I do think that there's a lot, like, we don't have, at least I don't have the data to suggest which is going to be the best. But I think in general, if we think about movement as medicine, there's a lot of really wonderful opportunities for movement.
Yeah, I think I agree. And I think it's personal, and each person find their own, area of motion that is more convenient. I don't like running, but I enjoy swimming, and I wouldn't go and train myself running and do all this. My husband did that as a young athlete. I never did it. As a young athlete, I just did swimming and so forth. But regardless, there is a commonality across all humans from birth, and is these abundant degrees of freedom that we have throughout the body, and the brain has to control them. It's over 600 degrees of freedom. The brain has to control them. And so one of the jobs of the brain is to learn how to economize and how to optimize the control of these degrees of freedom and this formation of synergies that then save energy, conserve energy. And one of the things we've learned when we study autistics and their movements throughout the body is that there is a lot of energy expenditure because the brain is not synergizing those muscles in the same way that a neurotypical individual is of comparable age or and so forth. And this poses a tremendous cognitive load to the brain. And we've measured this with EEG and with other means, because what happens is that in a neurotypical system, the brain doesn't have to pay attention to these things. It's just happening automatically for you. But in the autistic system, the brain has to pay attention to these things so that you don't fall or you don't, and in the meantime, it's recruiting all these enormous numbers of degrees of freedom and consuming a lot of energy to move, to just perform a simple task that we don't have to think about. So that's, if we could define a therapy that teaches the brain how to automatically recruit this synergies, these degrees of freedom in a way that is economical so not to have to pay attention to it, that would be ideal. And I think that we can move in that direction using these tools, because then gives us a way to see what we cannot see otherwise. This is invisible to the naked eye, but now we bring it up to the surface, and so we can modify it accordingly.
So just to reiterate that point, because I think it was a really important one, their nervous systems are working much harder to do things that a neurotypical nervous system would be doing. And so it's reasonable to think that they would need much more recovery and rest, because of this extra tax, we'll call it, on their system. Would you?
I would agree to that. It needs, I would give a little bit more time. It also in the early stages when autism is diagnosed, which is already really a long time that goes by before the diagnosis, and that the system is already coping with a difference and coming up with each one its own mechanism, so to speak, to overcompensate for whatever it is that was different in the development in the first 2, 3, 4 years even of development, of neurodevelopment. One of our jobs is to try to identify what it is that is working in that system already that the brain figured out, but at the same time, give it a little bit more time because the maturation path was different. And some of the expectations that we have for the maturation of the neurotypical system don't apply necessarily to the autistic system that took a different route. It's like took the scenic route instead of the shortcut, or it may have taken the shortcut instead of the scenic route. But in any case, giving it more time and considering that it's a different system that you're working with will make a whole world of a difference for the person that is being you're interacting with, to change something so that the person feels better.
Yeah. Okay, thank you so much. So another question was, do we keep doing activities on a repeated basis in order to teach motor skills?
It's a very good question. So I think that from the neuroplasticity perspective, repetition, it's this notion of like use it or lose it, or repetition to really do that training. But I think the thing is who is requiring the repetition? Is this some interventionist requiring the repetition of an autistic individual, or is it the autistic individual being like, I want to see if I can do a couple more repetitions? I, again, do not have data to suggest this, but I'm going to speculate that is going, if it's other imposed or self-imposed, that's going to have differential effects. I myself, when I'm told to do something more, maybe will not engage it as full throttle as if I myself am, wanting that as a goal for myself.
Mm-hmm.
I completely agree. And we do have data. Back in 2013, we did this experiment where we instructed through a goal, and led to many repetitions of this goal by presenting the match to sample task to match a sample. And then we contrasted that with evoking the goal so that the person would self-discover the goal and repeat it on a self-generated, self-initiated basis. And it was day and night. And the 25 non-speaking individuals in the spectrum that we tested, and we published this work already, not only did much better than when you were doing this on instructed repetition rather than self-exploratory self-evoked repetition, but also it transferred and generalized better to a different environment. So we came back 5 weeks later without any type of training in between. And the system picked up where it left, and it reached the point of self-discovery much faster than the group that it did it on instruction. And that did not generalize as well. So there is something about contextual variations that self-emerge from this self-discovery process that are fundamentally different from the variations that emerge from a goal-directed, intended, deliberate motion that you instructed the person to do. Both are good, and you need it. Both are needed. But we go back again to give it a bit more time in the exploratory phase so that you allow for a more relaxed environment and way to do things. Then you can go into the instructed phase that we all do, like when we take classes and so forth. So it's kind of preparing the system for it.
Mm-hmm. Okay, that was great. Okay, next question from April Humphrey. What types of autism symptoms were improved after the balance training?
Yeah, it's such a great question. So one of the things with this measure, so we had to specify this measure ahead of time, and it's a parent report measure that covers all the different aspects of symptom severity. So it has like social responsiveness, eye contact, repetitive behaviors. And what we found was that it was mostly the social responsiveness aspect from that measure that was related to the intervention. So maybe not so much the repetitive behavior and or restricted interest piece of things, but it is kind of it's kind of a conglomeration. It's a summary measure.
Okay, great. I wanted to give a quote that Sarah Siegel wrote before. And she said, like Einstein said, not everything that counts can be counted. Without collaborating with the autistic community, how could non-autistics know what is necessary to measure? And I think that's just, again, underlying the importance of what you said earlier about, working in collaboration with the community and not just deciding
Yeah. And we've had, lessons learned. I agree with that 100%. I think that research in everything is just so enhanced when we have diverse and neurodiverse perspectives involved. But when we first did this randomized controlled study, it was 8 years ago. I was pregnant with my son, and we put in measures that now I'm like, oh, that isn't good, right? So it's interesting to see how we've made mistakes and yet are evolving. And we're so grateful to the autistic community who our community advisory board, who we seek feedback on all these things now. So it's like lessons learned. Let's not repeat those, right? Let's really hear from the community, the autistic community, that this is something that's helpful, interesting, useful. So we're lucky to have that in place now where we didn't before.
I think that's such a testament though to your work, because like that humility is really necessary, in order to keep improving. Like that's how we all move forward, is being able to look back and see how, what we can do better and how we can be as inclusive as possible.
And I have to say also, as someone who came from a different field altogether, when I arrived first at autism field, I had no idea what experimental assay I was going to do. I remember visiting the Douglas Developmental Disability Center that invited me to collect data while they were doing their exercises. And I came with a whole list of things I was planning on doing, which came from my motor control research. And the therapist there said, good luck with that, because you're not going to be able to do any of it. So I said, okay, let's go back to and so I find that working with the autistic community it's a must, and I do that as a rule. And working also with the people who do the work of their therapeutic work, the teaching work, and so forth, and the parents. We work with the parents a lot. Can tell you a lot about that child, because they spend a lot of time with the child. And when the child cannot explain to you verbally or speak to you what it's difficult to design an experimental assay that will capture what you need.
Yeah, absolutely. I wanted to give another comment that Tanya had said, is that reducing repetitive movement, increasing eye contact, and changing so-called restricted interests aren't high priority for us, except for when we get stuck in a movement or activity that we don't want to be stuck in.
Thank you for that feedback. Yeah, it makes me really think about like how meaningful were those changes in our intervention, right? And how can we measure something that is more meaningful, like maybe the time spent in a repetitive activity that you don't want to be engaging in. Maybe from that comment, that would be one of the things we could look at in the future.
Yeah. And in general, I think autism research needs a bit of a pause so that they can ask these questions and get the feedback. And I'm just like, as someone in the community myself, like I'm always so grateful to researchers who, are open to listening. It's such a great quality, I think. And okay, so
I have to step out because I have another call. This was amazing. Such an amazing research, and I'm so grateful that you came to give the talk, and I look forward to continuing the conversation.
Absolutely. Thank you so much for the invitation. This is fabulous.
Of course. And I can just leave, right? Nothing will happen if I... Yeah. Okay, good. Okay. Thank you, guys. Bye.
Thank you, Liz.
Bye.
Okay. I was just going to give you another comment here. It says, such an amazing talk. My child takes great pleasure pouring from one cup to another, and I wonder what she's working on brain-wise. interesting if things kids get stuck in is actually something their body and sensory system needs. And I feel like a lot of the time that is the case. And then other times, like there's a lot of self-reports that that's not the case. They actually do not want to be, doing the things that their bodies are doing and feel almost, like they can't stop their bodies from doing it. Or alternatively, that they can't initiate to do, many things as well. Do you feel like, is this something that could be improved no matter what someone's age is?
That's a great question, Jen. So yeah, I mean, to get to your point earlier, I think, unless it's really hard from the outside to know if that's a movement that people want to engage in. Mm-hmm. I always presume that it is, unless there's signs that there's some type of distress. But I actually wonder if measures like heart rate variability or something that could show kind of like arousal or might be related to more of a stress response might be able to actually distinguish some of that in the future. Sorry, and then remind me of your question again. I remember it was brilliant.
I think it just was a matter of, as far as initiation and also, stopping a motor activity. Do you think that, like, if someone's even 45, is there potential for that to become more refined, even if they aren't extremely young?
Yeah. So I would say that yes, I think that our brain never stops changing, but from the neuroscience literature, well, and if you think about some of the anecdotal reports and even the science, you have 80-year-olds learning tennis, right? Like learning new motor skills for the first time. Yeah. And isn't that amazing? So that our brains continue to adapt to these new skill sets that we want to learn. But we do know from the neuroplasticity research that young brains are more plastic than older brains. Mm-hmm. And so if you think about things like language learning and some of just how a young child can learn so quickly and learn the accent, and it just seems so natural, right? Yeah. Enviable, really. And how that can be a little, you can still gain that proficiency. It just might take a little bit longer as an older person. So there's hope, but it might be a slower, longer progression.
Mm-hmm. Yeah, like for any of us.
Exactly.
I wanted to ask an interesting question that Tanya had also asked before. She said, many of us treat our sensory hypersensitivity with magnesium and potassium based on research into channelopathies. This either ameliorates or eliminates sensory overstimulation depending on the severity and cofactors. Are the neurons in the brainstem typically the ones affected by ion channel issues?
That's such a good question. I don't know, but I can look into that. So thanks, Tanya. And if I can either look it up or you can send me an email because I really want to follow up on that because I think it's a really interesting hypothesis.
Okay. Tanya, if you want, you can email me and I can give you Dr. Travers' information. I think that's a great question too, and so interesting. And motor seems so complex, obviously.
Yes.
And Dr. Torres has talked a lot about this as well, and you both kind of mentioned this before, but these differences are there, from such an early point, and they're not in the diagnosis. And, the behavioral signs don't really discuss or, describe these differences really. But as far as like supporting these differences, is an occupational therapist like the person you would suggest would have the most background on this. I know, like, there's music therapy and things like that. Those things aren't really covered by insurance at this point for the most part. But I think hopefully as more people become aware of these motor differences and the prevalence, this is something that, will hopefully be more available, for supportive measures, right?
Yeah, and that's my hope too. So if I were thinking about this, I'd probably, like, either for myself or for my child, I would think about probably an occupational therapy or a physical therapist might be a good way to start.
Mm-hmm.
But I think that, kind of how we touched on this before, there's a lot of different pathways into this. And a lot of it, like particularly in occupational therapy, an occupational therapist is only supposed to work on things that the family wants or that the person wants, things that are important to them. So if motor things are not, like, motor differences aren't an important difference for a person, then they won't work on that.
Mm-hmm.
So if that's brought up as a concern for the person, then that's something that can be tapped into. But I think sometimes, like, at least when I go, I was really surprised. I'm not an occupational therapist, but I work in an occupational therapy program, and I'm really inspired by the occupational therapy philosophy of really thinking about meaningful actions and occupations, which are the things that we do in our daily life, as both intervention and outcome. That we do better when we are engaged in tasks that are meaningful to us. But so I don't think I would have gone to an occupational therapist and been like, oh, these are the places where I would like to work. I would have kind of waited for them to diagnose me or things like that.
Yeah.
But now, knowing what I know, going in and thinking about, like, this motor difference bothers me or doesn't, right?
Right.
And being able to direct that care, because it should be in partnership.
Yeah, 1,000%. I'll give just one last comment and then we can get going. But Femme Intangible says, it's amazing how several sleepless nights will show just how much the brain is doing that we're constantly taking for granted. Constant struggle over millions of tiny things and then even bigger burnout. And I think that is it's so true, because you mentioned earlier about what it must feel like, to be experiencing these things. And not only to be experiencing them, but in a society that misunderstands you, on top of, having these internal struggles and this, extra cognitive load, like Liz mentioned before. And so I think it's like, having work like this available and, like, being able to learn more about how all of our systems actually work is, like, really important in, not only for empathy, but in, more supportive care and more person-centered care. And so, we are very grateful for work like yours that's, like, really moving things in the right direction.
Well, thank you. This is so fabulous. It's so great to get to talk with y'all, and thank you for the fabulous comments and questions. And it's good to know. It's good to get this feedback, essentially. And so if anybody has additional feedback, we're open to it. We're ready for it. We want this work to be impactful, and that means that we want to get feedback early and often from the autistic community.
Wonderful. If anyone would like to contact you, I guess they can reach out to me and I'll pass them along.
That'd be great. I also have my information on this last slide too.
Okay.
If anybody wants to put it on the,
okay.
There we are, btravers@wisc.edu.
Okay, perfect. I'm going to put that in the chat as well.